Hello, everyone. I'm Scott Constable. This is my colleague, Raju. And just want to begin by saying, so today my manager is presenting in Hawaii at a conference. And when we learned that she's going to present in Hawaii and I'm going to present in London in December, we concluded that one of us was the lucky one. But I have to say, after going through the process of preparing for Black Hat, seeing all the effort that it takes to make this Herculean event come together on account of Christina, Lydia, everyone else who was involved. I'm really humbled to be here, really honored to be here with my colleague Raju on stage to talk to you about a technology that both of us love a lot, Intel Trust Domain Extensions. And there are just three co-authors on this briefing, but there are a lot of other teams that work together to launch this product, to continue to enhance it. And also we want to acknowledge the researchers on an earlier paper that was presented at ACM CCS this year, titled TDX Down, who allowed us to use their POC in some of our demos today. I'm going to begin by walking through some of the background information. I'll talk about confidential computing, Intel TDX, side channels, and a technique that can be used to maliciously single step, so execute a single instruction at a time in a trusted execution environment. And we'll talk about what trusted execution environments are. Then Raju is going to take over and talk about some early prototyping that we did to mitigate these kinds of attacks in a pre-production TDX environment. Then I'm going to take over, and we're going to go through some demos that show how these attacks work in practice and how they can be mitigated. And finally, we're going to compare with the defenses in Intel's other trusted execution environment, Intel SGX. So this talk is fundamentally centered on a concept called confidential computing that addresses a long-standing gap in traditional security and privacy technologies. So these traditional technologies for a long time have been able to protect data at rest, like in storage, using techniques such as data encryption, and protect data in transit, like over a network with technologies such as TLS and HTTPS. But the gap has been protecting data that is in use while it is being processed by a CPU, while it resides in the main memory. And that is the gap that is addressed by confidential computing. And the specific driving force behind confidential computing for the past decade has been trusted execution environments, including Intel TDX and Intel SGX. This talk is going to focus on Intel TDX. Which is a confidential computing technology that provides confidentiality and integrity for virtual machines. And we call virtual machines that are protected by TDX, we call them trust domains, or TDs. And Intel TDX is backed by a TDX module, which is a new piece of firmware that acts as a kind of co-hypervisor to the hypervisor that would be enabled on the platform. So today, these are typically being enabled in cloud service providers to facilitate confidential VMs, such as TDs. And TDX enforces security properties that protect the tenant software running inside of a TD from all other software that resides on the system, including the most privileged software, such as the host hypervisor, and from all other tenants on the system. TDX assumes a very, very strong threat model, and therefore has a relatively small trusted computing base that includes just the TDX firmware, the underlying processor, and some additional components that are used for remote attestation to allow a client to attest that the client's expected code and data is residing in a remotely attested environment, such as one that would be hosted by a cloud service provider. Everything else is outside of the TDX threat model, and that includes some physical attackers, such as a rogue system administrator who might have some degree of physical access to the machine. TDX has a variety of mechanisms that enforce these confidentiality and integrity protections. So just to give a brief overview, if you have any questions, want to discuss this afterwards, Raju and I will be available during lunch. Please feel free to come up and talk to us. For example, if any other piece of software on the system, including privileged software, tries to read private TD memory, it will receive a fixed byte pattern from memory. So it won't even see ciphertext, no chance of trying to choose a chosen plain text attack. If other software on the system tries to overwrite private TD memory, it will poison that memory in one of several mechanisms. And if a TD later on tries to read or execute poison memory, the TDX module will shut down that TD. It'll assume that the TD has been compromised and it won't allow it to access any further. Now, those protect the data itself, the plain text data within the TD, from any confidentiality or integrity violations. But what is not included in the TDX threat model is some kinds of side channel attacks. So what is a side channel? Side channels arise from fundamental resource constraints in modern CPUs. They have a finite number of caches, of buffers to keep data, and they might have many different tenants that have to be co-hosted and running concurrently on the machine at a given time. So these microarchitectural resources that are not visible to the software are being dynamically shared in a way that's transparent to software to provide very good availability and quality of service. So in this example, suppose the attacker is doing something with the teapot, and the processor has allocated some buffer for the attacker to do its teapot things. And the victim is also doing some confidential computing on cat things. And in this instance, the attacker and the victim are sharing this hardware buffer. And so when the victim wants to do a cat thing, it needs to get that buffer. This is demand sharing. And the hardware will invalidate the data or clear the data that the attacker was using so that it can make space for the victim's cat thing. So, and then if the attacker needs to do another teapot thing, then, because the hardware had taken that buffer from the attacker, it must now give it back to the attacker so that it can do its teapot thing. And the attacker might notice that when it does the teapot thing, it took a little bit longer because it takes some time for the processor to give the hardware buffer back to the attacker. Now, if the victim does something else, not a cat thing, then the attacker tries to do a teapot thing again, it will be noticeably faster because the hardware didn't have to take the hardware buffer from the attacker. And then suppose the victim does a cat thing again, maybe with a different cat. Then the attacker tries to do its teapot thing again. Teapot is again slow, so the attacker is able to infer that, oh, the victim must have done a cat thing. Now, I want to emphasize, the attacker cannot see the plain text that the victim's operating on. It can't see the picture of a cat. It can't tell that the victim is doing a house cat thing or a lion cub thing. But it might at least be able to infer whether the victim is doing a cat thing or something other than a cat thing. And in some security contexts, this might be interesting. The attacker might be able to learn something useful. However, in practice, this is very challenging to make use of, in part because watching a TD using these hardware buffers is like trying to watch a pinwheel that's spinning very fast and trying to make sense of it. Because the processor is executing billions of operations, billions of instructions per second, and these side channel measurements become very noisy. It's difficult to make sense of. So what if the adversary just triggers a single operation, like giving the TD a network packet, just one operation at a time, and performs a side channel measurement? So that's sort of like taking a picture with a slow camera shutter. So even observing millions of instructions at a time, not very easy to filter through all that noise. And you get a very noisy image, and it's in general very challenging. But let's try something more precise. Can the adversary trigger just a single instruction at a time, like using a debugger like GDB? So if the attacker could do this, then maybe the attacker could step by step observe one instruction at a time. Did the victim do a cat thing, or did it do something else? And in fact, this technique was pioneered and demonstrated in a framework called SGX Step that established this for Intel SGX, and this was published back in 2016. So what those authors did is they looked at the Intel Software Developers Manual, And they noticed that there's this feature called the Advanced Programmable Interrupt Controller. And that controller includes a programmable timer that is available to software to time events or operations. And it has a mode that allows software to use the local APIC to signal an interrupt at an absolute time. And maybe they thought, that's interesting. So maybe if we know that the first instruction executes exactly 5,000 cycles from when we arm the timer, then maybe we can arm it so that it interrupts that first instruction and causes just that one instruction to execute, then exits the trusted execution environment. Then we can achieve a sort of single stepping, almost like using a debugger. Well, it doesn't quite work out of the box because if you try doing this, you'll see that the SDM, it doesn't work quite as well as the software developer's manual would suggest. There's a lot more variability in the accuracy of this APIC. And there are 3 reasons for this. The first reason is that the APIC timer frequency uses the core crystal clock, which is not part of the individual CPU cores. It's uncore. It's elsewhere on the SoC. And it's a much lower resolution than each of the physical cores, by about 2 orders of magnitude or more. And it tends to drift from each of the individual compute cores. The third reason is that on these modern processors, they execute instructions in a superscalar manner out of order. And that means that a lot of operations happen in a non-deterministic amount of time. So one time you enter a trust domain, takes 5,000 cycles, the next time 5,500 cycles, and you can't predict or control exactly how long it's going to take. So all this adds together to be rather challenging. However, the SGX step authors figured out an interesting solution. So they noticed that when entering an SGX enclave, SGX flushes all of the virtual to physical page translations from the translation look-aside buffers. And what that means is that after entering an enclave, every instruction that executes has to go through a page table walk, or at least the first instruction does. And that takes some time to get the physical address. Then there might be some other microcode assists that have to happen, like to set an access bit on a page table entry, and that takes some more time. And eventually, all this extra stuff that has to happen for the first instruction may make even a no-op that you think takes 1 cycle, the fastest possible instruction. That might actually end up taking hundreds of cycles, which makes it a big enough target to hit with the APIC. So the first key idea from this presentation is don't try to hit a small target. Instead, make the target slower and therefore bigger. Now, Roger's going to take over and talk about some early prototyping that we did with TDX to try to mitigate this attack vector.
Thank you, Scott.
Yeah.
Hey everyone, good morning. I am Raju here, and I'm an offensive security researcher with Intel. My team and my focus area is primarily looking into how to break some of these technologies rather than building. And when we came across the SGX step attack for the first time, our team was given a charter to go ahead and see how this can implicate the Intel TDX technology, which was still under development 3 years ago. And that's when we got engaged to really create something called a proof of concept to demonstrate the exploit to see whether SGX step is really a feasible attack for TDX. So we want to look into the TDX step attack scenario. There are 2 things we considered. One is we have to develop a proof of concept because we never had a TDX-enabled platform at that time. And as we know, the trust domain extension technology is built on Intel's VMX, or virtual machine extension, which relies upon the virtualization. And we needed to use a virtualization setup. And secondly, as Scott mentioned, the SGX step attack was demonstrated by abusing the APIC timer on the platform. And that is where we also wanted to reproduce the same attack for TDX. And this is how the attack scenario looks like, where we have a malicious VM or a untrusted VMM, which can actually abuse the APIC timer to malconfigure it in such a way that it can cause the interrupt on every instruction boundary of the VM or the victim VM which is executing. And when we set up this kind of a attack scenario, we will be able to cause the VM to do VM exit on every instruction boundary, and now the VMM has the control of VM execution. And I'm going to step you through some of those details in the coming slide. So for the pre-TDX test setup, as I said, we never had a TDX-enabled platform, but still the job was to showcase that this attack is feasible. And the step we took, first of all, we use the KVM as the host, and the KVM host, which is untrusted for TDX attack scenario, but we also leveraged a portion of the KVM to behave like a good VMM, which essentially detects the step attack and also be able to mitigate the attack so that the VM is secure. And the bad VMM is the one which is essentially causing the epic timer configuration and causing those periodic interrupts. And coming to the VM or the guest OS, we used a Ubuntu VM as a guest OS, and we were running a string length application of 34 instructions to keep it simple so that the intention was to demonstrate that this attack is feasible. And eventually, whatever the code that we developed as part of the good VMM in the KVM that was taken as a reference code and implemented inside of the TDX module, which is a trusted entity and a secure software that is able to maintain the TDX security objectives. So I will show how we managed to do that in the TDX module in coming slides. So now we will see how we managed to realize the TDX step attack. As I showed you earlier, the bad VMM configures the epic timer to cause the periodic interrupt. And now, on every interrupt, by design, the VM has to exit to the host through VM exit. And now, if the VMM has configured the epic in a way that it interrupts on every instruction boundary, the VMM will get the control of the VM execution on every instruction boundary. Not only that, the VMM will also be able to do some micro architectural analysis as part of that, and in turn, it will also cause the VM resume to make the VM to continue the execution of all the instructions until it gets exhausted. So that way, it has the full control over the execution of VM. From a result perspective, as you see, the interrupt-based attack string length, the victim VM was running the string length application, which was having 34 instructions. And we ran the experiment maybe for around 100 times. And as you see in the graph, we managed to hit the success rate of around 8, which means that around 8 times we are able to get all the 34 instructions in a correct order. That demonstrated that indeed this step attack on TDX architecture is real. Then once we prove that this is a valid attack, we have to work on the mitigation as well. And we came out with 2 proposals. We started with the first mitigation, where the mitigation was implemented with the help of the good VMM and also a VE handler or a virtualization exception handler, which is running inside of the TD. That means whenever the good VMM is able to detect that the given VM is under step attack, it will send a notification to the VM saying that you are under attack, so you have to manage this virtualization exception. And then the VM will manage this VE handler, which is essentially running some arbitrary random instructions, and then return the control back to the bad host. By doing so, what we are preventing is the VM is not going to execute the real instructions at that point. Rather, it is running some arbitrary instructions. So that way, even if the bad VMM runs any side channel analysis, it will not be able to get to the real instructions that VM is executed. So from a POC result perspective, this is what the outcome was, where we ran the test and we managed to show that with the mitigation, we are not able to get to the 34 real instruction at any point of time based on the number of experiments we did. And however, this mitigation has 2 limitations, as you can see. Right? The first one is the scalability, where the mitigation required support from the TD implementation or the TD owner. He or she has to implement this VE handler and make sure that it is working correctly. And in a real world, it is not scalable. And the second limitation is also because we are bringing the TD into the trust boundary of the mitigation, it also increases the attack surface. So the challenge is, how can we still meet the same security objective but overcome these limitations? And that's when we came out with mitigation proposal 2, where the mitigation was implemented fully self-contained within the good VMM, which is eventually became part of the TDX module implementation. And also, because the implementation is inside the good VMM, the attack surface is only restricted to TDX module. And also scalability is not an issue because the same module will be deployed across any VMs or any platform, so the scalability is also addressed. And what happens is, when in this model, when the good VMM detects, it implements a step filter detection algorithm based on which it will detect that the VM is under attack. Instead of sending a notification to the TD or VM this time, it will basically implement a random VM resume instruction for X or N number of times so that the VM implements or executes some random instructions, just like the previous one. But only after that N instructions, the good VMM will return the control back to the host, which is bad. That way, it is hiding completely the real instructions that were executed by the VM. And from the result, we were not able to, anytime with this setup, the 34 instructions were never able to seen by the host VMM, thereby defeating the attack. And this is my last slide. So as I said from the beginning, the good VMM portion of the implementation was eventually ported to TDX module. And Intel TDX module, the good thing is we have also made it open for the auditing to the external researchers or industry partners, which is available in this GitHub link. And this is the step algorithm that it actually implements, where it is a heuristics-based implementation, where it implements this VM step filter algorithm. There are two conditions based on which the TDX module will detect whether the TD is under step attack. The first one is it will basically make sure that the interrupt occurrence of the current TD versus the TD enter, if that number of cycles consumed is less than 4K cycles, then it will determine that this TD is under step attack. And we use the TSC or timestamp counter to measure these cycles. And my friend Scott is going to talk a little more detail on TSC later. And we also look at the return instruction pointer to make sure that if it is not progressed, then the TD is also under step attack. Based on this outcome, it will basically cause the VM resume to execute some random number of instructions so that the TD will not be able to execute the real instructions at that point of time. Based on this mitigation, we were able to prove that SGX step attack is feasible on TDX architecture, but we also came out with a mitigation to defeat that purpose. And interestingly, from security research, we always want to make progress, and there are different attack scenarios that one can think of. And Scott is going to talk about how we managed to also defeat this mitigation and make it more stronger in the next slides. Thank you.
Thank you, Raju. Now let's get into some demos. But before we do, I'm going to dwell on this diagram a little bit, this dart-throwing metaphor. We're going to keep returning to this to show how each demo is a progression on the previous one. So this dart-throwing metaphor, the attacker is throwing darts, right? And the darts are APIC interrupts. And the attacker has to throw it over the operation that enters the trusted execution environment and tries to hit the first instruction that is executed after entering. And the goal of the attacker in this single stepping is usually to try to make the target as big as possible so that the interrupt is likely to land on that instruction and cause it to execute and then trigger an exit. So progressing from single-stepping SGX to trying to single-step TDX, the attacker encounters some additional challenges. So the first challenge is that the page tables in TDX are isolated. They are protected within the trust domain's private memory. So the attacker can't manipulate metadata on the page tables to try to trigger additional microcode assists that might add latency to the instruction. The second challenge is, as my colleague Raju just explained, that there's a built-in mitigation now that the attacker has to contend with. That if the attacker launches the attack and tries and triggers the instruction to exit too soon before a certain amount of timestamp counter cycles have elapsed, then the mitigation will be triggered and force a random number of instructions to execute. So let's just try to single step through a TD without doing anything else and see what happens. So in this demonstration, there are two windows. On the top is the attacker, and on the bottom is a victim that's running in a trust domain. And it's going to take a few seconds to boot up, but I'll talk through the example while it's booting. So the code that's shown on the left here is an assembly instruction snippet, and it's going to execute a loop 10 times. Each loop iteration has 6 instructions, and there's an additional kind of boilerplate instruction at the beginning and the end. So in total, this instruction snippet that's going to be under attack executes 62 instructions. And the attacker's goal is going to be able to try to single step through this loop. So the attacker ideally should be able to measure 62 instructions each time. And right now, the single-stepping attacker is taking some measurements, and as you can see, they're not correct. So the first attempt had 5 instructions measured, then 7, then 4, 3, 6, 5. Those are not the correct measurements. Each one should show 62 instructions. So what happened here is that the mitigation was being triggered because the interrupt arrived and the enforcement mechanism detected, oh, you didn't execute at least 4,000 cycles, so I'm going to force a bunch of instructions to execute at random. And between 2 and 32 instructions execute, the mean of that random distribution is 16. So if you want to explain why the attacker made these measurements, take the total number of instructions, 62, divide by about 16 that are being forced to execute each time, and you get roughly 4. And that's about what the attacker is observing. So this shows that the mitigation is working as expected. But now, as I mentioned earlier this year, there was a paper called TDX Down that was published in ACM-CCS. And the authors of that paper noticed something else that's kind of interesting in the Intel Software Developers Manual, that newer processors have this feature called invariant timestamp counter. And the SDM says the invariant TSC will run at a constant rate in all ACPI states. So it's talking about frequency scaling and sleep modes, et cetera. And newer processors have this, so they tried to think about, okay, maybe is there some way we could use this to circumvent that timestamp counter heuristic? And it turns out they were successful in doing so. So they observed that by slowing down the victim core, that in this case is executing a program within a trust domain, by slowing it, for example, from 1.8 gigahertz to 800 megahertz, because of this invariant TSC property, that causes the latency of all operations executed by the trust domain to increase by a factor of 2 or more. So on our test machine, all the victim operations would increase by a factor of 2.25. And it seems like that's just enough, in fact, to exceed the threshold of that built-in mitigation, to make entering the TD plus executing an instruction plus exiting add up to more than 4,000 cycles. And we'll show that in this demo here. So at the bottom right, you'll see I'm running HTOP now. And HTOP is showing the frequencies of the core. So the attacker is running on logical processors 2 and 130, and the victim is running on 1 and 129. And what the attacker just did is invoked a script that descales the frequencies of the victim core, and you can see the victim core just dropped to 800 megahertz. So now the victim core is running slower, but the TSC is running at the same rate. And so that's going to affect the effectiveness of the mitigation. And so now you see when the attacker runs the exact same attack program, the attacker reliably counts the exact number of instructions, 62, 62, 62, and then once with 63. So it's not 100% accurate, but it's pretty good. It's like 98, 99% accurate. So the second key idea from this presentation is that frequency scaling can be used to fool mitigation heuristics that rely on the processor's timestamp counter. Now there is another way to circumvent this mitigation that has not been previously published. This is something that we discovered internally. So this is, again, the dart throwing diagram, and that bar at the bottom shows how TDX down works, as it slows lots of operations. But let's go back to key idea 1. Don't try to hit a small target. Try to make the target, and only the target, slower and therefore bigger. So is there something that we can do here, like in the page table walk? Now, I really love this diagram. And I love the title of this slide, too. So the blue line at the bottom shows how bare metal processes, so non-VMs, translate from linear or virtual memory to physical memory addresses. They do a page table walk. And the page tables are somewhat shallow. You walk through usually 4 levels of page tables to get from a virtual address to a physical address. But if you're executing inside of a VM, the square of that number of operations has to occur because each level of the page table hierarchy must itself be translated from a guest address to a physical address. So you might have to perform, I think, 20 operations, and these cannot be parallelized. This happens serially, one after another. You have to perform as many as 20 operations to go from a guest virtual address to a physical address. Normally, this is very, very fast because these addresses are cached, but in the worst case, if those translations are not cached, and if the processor has to do an extended page table walk, and those page table entries aren't available in the CPU's caches, it will have to go to memory to get the first address, to get the second address, to get the third, to get the fourth, to get the fifth, all the way up to the 20th. And that can take a while. On many processors, it might take several hundred. I think on our test platform, about 750 cycles to go to memory to get some data. So multiply 750 by 20, and you get a rather large number. And you can end up making a single no-op very, very, very expensive to execute if you do this maliciously. So in our third demo, let's attempt to single-step a TD by flushing the EPTs. And I tried making this into a demo, but the process of flushing all these EPTs takes a long time. So the demo runs, but it takes about 10 minutes. I couldn't quite show it here. And the code to enable this demo is fairly simple. We wrote a kernel module that plugs in, and before invoking and arming the APIC, it invokes this instruction called write back and validate, which flushes all of the CPU's caches and takes quite a while. So you have to sleep for a fraction of a second for it to complete. And what that does is whatever PTEs and extended page tables the TD had previously used, those will all be flushed. So when the TD has to do a page table walk again to find its instruction memory, to find its data memory, it's going to have to keep going to memory to do all of that. And when we run this demo, it's pretty accurate. You can see it does circumvent the mitigation. That instruction will take a very long time to execute. It's not quite 99% accurate, but I think when I did my own pencil and paper calculation, it was about 96, 97% accurate. So now how do we mitigate this? How do we address this problem? So the newer versions of the Intel TDX module, which is firmware, so it's continuously being upgraded through the Intel platform updates that we release at a regular cadence. There's a new feature called instruction counting single-step defense, or IC SSD, that instead of using the timestamp counter as a proxy for forward progress within a trust domain, uses a performance counter that measures instructions executed to retirement, so instructions executed to completion. And if the TD doesn't execute enough instructions to completion, then that mitigation enforcement will be imposed by the TDX module. So in this last demo, we'll show how again, the TDX down technique, the frequency descaling. So the attacker in this case has already descaled the victim's CPU frequency to 800 megahertz, and now is attempting to execute the same single-stepping technique. And yeah, so as you can see, it's just like the first demo. The mitigation was activated reliably, and now the attacker is only counting an average of 4 instructions per attack attempt, which is incorrect. So finally, we're going to close with a comparison to another mitigation that we implemented for Intel SGX. This was introduced a couple years ago, and we presented it at the Usenix Security Symposium last year in 2023. And this mitigation is called AEX Notify. It's different from the from the ICSSD, which I'll explain why that is. But I'll return to this dart throwing diagram again. Remember, single stepping in SGX enclave is facilitated by the page walk and the A-bit assist, makes each instruction take a while after entering an enclave. So what AEX Notify does is it slightly tweaks the behavior when entering an enclave. So you don't resume at the previous instruction where execution had stopped. Instead, each time an SGX enclave is entered, it passes through a kind of what we call an AEX Notify handler. And it's a software routine that preemptively kind of warms up the enclave and preemptively triggers page table walks, microcode assists ahead of time before jumping to the application code that runs inside the enclave memory. So why did we implement two very different single-stepping mitigations for Intel SGX and Intel TDX? So fundamentally, it's because they're two very different technologies. So SGX is a process-based technology, and SGX Enclave is a region within an application's memory. So if you could imagine, like, loading an SGX enclave is sort of like loading a DLL or a shared object. The application loads it and then calls into it and calls back out of it. It's a part of a process. Whereas TDX is a virtualization-based technology that hosts an entire virtual machine within a TD. And because of that, there are some consequences when we try to mitigate implementations for them. So notably, popular operating systems such as Linux can't accommodate a software handler that can run at arbitrary times, because there are certain critical sections of code that run inside the Linux kernel that cannot be interrupted, and in such a way where they'd require some event to be handled. So that was a fundamental limitation when we looked at Proposal 1, which Raju presented, where we thought about maybe doing this for Intel TDX. It occurred to us very early on that this approach would not work for TDX, and so we eventually went with the mitigation option 2, which was to implement the mitigation entirely within the TDX module. So here's our conclusion with some takeaways, and Raju and I are more than happy to stay up here afterwards for some informal Q&A as well. So first of all, confidential computing has a very, very strong adversary model that has proven, I think, very interesting and exciting for security research. This has opened up an entirely new frontier with these very, very strong threat models. And there are three really good examples from this presentation. So one is the privileged software has access to these privileged capabilities, such as using the advanced programmable interrupt controller, also scaling, descaling the clock frequency of a victim CPU cores, and finally, the ability to flush all of the CPU's caches on demand. But defense in depth mechanisms such as ICSSD and AEX Notify can help to mitigate any potential side channel attacks against trusted execution environments. And finally, modern processors use a variety of address translation caching techniques to dramatically accelerate memory accesses. I think one possible takeaway from the slide I showed about the page table walks is, oh wow, this can be really, really slow. But in reality, the normal case is that it's actually very, very fast. The processor does an enormously good job of dealing with the complexity of virtualization translation. And so in the normal case, instructions do execute one cycle at a time. And that's because of some very careful engineering that has evolved over several decades. And I'm always very impressed with what modern processors can do. And I've been very impressed with Black Hat so far, and I know Raju and myself are looking forward to all the other briefings and events over the next couple of days. Thank you so much for being such an attentive audience. I had a lot of fun presenting, and yeah, we'll be happy to take any questions. Yeah, if you could go up to the mic.
Thanks.
Nice talk. A trend we've seen a lot is basically using machine learning models to boost the signal to noise from a very low bandwidth side channel. Why do you think that only seeing one instruction is sufficient to prevent a side channel attack? What would happen if I could reliably stop at 2 instructions and then be able to start learning the behavior of the instruction that I'm trying to recover information from the trust domain?
Yeah, that's a really valid point. So what I'll say is that there's no trusted execution environment that can comprehensively mitigate side channels. It's not really a solvable problem as long as you have multi-tenant systems that share hardware resources. The only way to close side channels is to not share, and that is very costly. So the best that we can do is have as much defense in depth as possible without impacting the key performance indicators like availability, like performance. And so that's what we've attempted to do with both the single stepping mitigation for Intel SGX and the ICSSD for Intel TDX, is that we think those are the best mitigations that we can possibly implement without having a negative impact on the way trust domains, SGX enclaves are used. So you're right, no, it doesn't comprehensively mitigate side channels, but what I could say is just imagine you're using GDB, and the GDB version you're using doesn't allow you to single step through your program. It forces you to execute a random number of instructions each time. It would be very frustrating, right? So that on its own is just raising the bar to make it more frustrating to try to get meaningful information from trusted execution environments. And if we can do that with basically no cost or virtually no cost to the end user, we think that's worth doing.
Hi guys. Just touching on that, Scott, yeah, on these mitigations, have you released any papers on actually performance impacts of any of these mitigations, like the step filter, for example, for TDX? What's the impact for that in the TDX module?
Right. I don't know about the performance impact for the TDX module. Do you, Raju, have any information about that?
So from performance perspective, the step filter will take into action only when the attack is really in place, right? And we have measured in terms of it doesn't have any additional latency by introducing this mitigation into the TDX module because we are also relying upon the hardware. Earlier, we were relying upon the TSC. Now, with the performance counter, the TDX module is the most privileged software on the platform, and it has direct access to the hardware. So it does not, we have not seen any performance implications because of this mitigation when it was introduced.
I could add a little bit to that, yeah. So the TDX mitigation is really triggered only when the TD executes for a very, very short amount of time. And in benign scenarios, that should really never or just about never happen. Yeah. The SGX mitigation is invoked each time the enclave is entered, but it also has a very low latency. So in the paper we published last year, we did publish performance numbers, and we estimated that the maximum impact to the workload should be no more than 0.4%. That was the most conservative estimate.
Any other questions?
Because you're injecting at least 2 instructions, once you detect this, does this then allow, if I continually trigger this attack, to completely halt any forward performance of the victim VM? Right, so I'm gonna try to single step, an instruction is not gonna go be processed, so it's gonna inject 2+ random instructions. I'm gonna stop after 1, and it's going to continue just to stall at that point and only execute your random instructions without ever making forward progress on the victim workload?
Yeah,
Okay.
yeah, that's it.
All right.
All right.
Thank you very much.
Thank you so much.